Good morning, good afternoon, good evening, mammals. This video is getting posted on Tuesday, April the 21st, and it's the second in a three-part video series on thermodynamics and kinetics. In the first video, I talked about enthalpy, which is the amount of energy stored in bonds. Today I'm going to be talking about another factor that's called entropy, which is a measure primarily having to do with the state that the molecules are in. And then the mathematical combination of those two, which is called free energy. Yesterday, when I talked about enthalpy, we classified reactions as being exothermic or endothermic, whether they had to absorb energy to happen or whether they released. And we talked about that the exothermic direction is favorable because it already has all the energy that it needs to make its products, whereas the endothermic reaction is not favorable because it has to absorb energy from the surroundings. But that's not the only factor that determines if a reaction is possible or not. The second factor is entropy, and its symbol is S, and I like to think of its symbol as S because its state is the primary thing that determines it. What it's measuring is how dispersed or randomly arranged the energy that the particles have is. And we say that nature prefers randomness, so changes that spread the energy out across the most number of molecules are going to be favorable. It isn't that nature favors these things or has any feelings about it. It's just that if there are a number of ways to arrange the energy, whichever one is going to be the most likely to happen is going to be the one that tends to happen because these are going to be random arrangements. Let me give you an example using money to try and make that clear. Let's say we have 10 people, and we are going to randomly distribute $10 between them in dollar bills. If we have $1 bills, we can give each person $1 and get the $10. If we're distributing $5 bills, then two people can get them. And if I'm distributing a $10 bill, only one person is going to get any money. And then there would be some combination of if I have a $5 bill and five $1 bills, then like 6 people could get some money. So if these things are going to happen randomly, the one that has the most possibilities is every person having a little bit of money because there's more combinations of $1 bills that I can distribute between 10 people. This is going to be the most likely scenario where everyone has a little bit of money because there's just simply more ways to arrange that. Whereas if I'm distributing one $10 bill, there's really only one way that can be distributed. One person can have the $10 bill, everybody else has nothing. It's like, how many ways are there to be broke? There's only one way to be broke because there's only one way to have $0. But there's a much larger number of ways to be rich because you can have many, many different combinations of, $1 million and be rich. So the situation that occurs is the one where you have the energy distributed most widely by the in small amounts among the most number of molecules. The ones that are least likely are one molecule having like all of the energy. So putting that back in chemical terms, states of matter like gases and liquids are more random because now the molecules have the freedom to move and they can disperse this energy in lots of ways. There are more ways to arrange gas molecules than there are to arrange solid molecules, because solid molecules have to sit there in a little lump, whereas the gas molecules would be free to move around. And so this has more possibilities than being a solid. So the main thing that you're going to be looking for are changes that turn solids into liquids or liquids into gases to go to a more randomly distributed state of matter. You can also do things where if you have one large molecule and you break it apart into smaller molecules, that's also going to be more randomly distributed, because here we have all of our energy confined within one molecule versus this. Now we've got our energy being distributed between two molecules. So the main things to look at are states, and if you can't make a decision based on states, then look at the thing that produces a larger number of molecules. Let's get some examples here. Okay. This reaction is going to have a negative delta S because I lost gas. My gas, my more random state, turned into a solid. Okay. Here I have two solids turning into a solid and a liquid. This is going to be a positive delta S because we made a liquid. Okay. This AQ, that's for aqueous, that just means dissolved in water, so we're going to treat it like a liquid. Aqueous and aqueous, so three total aqueous things. There's two aqueous here, and there's one aqueous here. Turns into a solid and two aqueous. So this one is going to be negative delta S. We lost an aqueous state, and we made a solid. A solid plus two more solids, so three solid molecules, turns into an aqueous molecule and two gaseous molecules. So this is going to be positive delta S. We made aqueous and we made gas. Two gas molecules, one gas molecule turns into two gas molecules. So here we've got three gases turning into two gases. So this is going to be minus a negative delta S because we lost gas. So I'm looking at the states, gases, solids, aqueous, or liquids, and then I'm looking at that along with how many that I had. If you looked at this and you only thought about the state, you would just say, oh, I've got gas and I've got gas, no change. What you have to do is get a little bit deeper and see that I've got three gases turning into two gases. So I lost a gas. So not only the state, but how many. So we've got these two factors, and they can either be favorable or unfavorable. So how do we decide which one wins out? In a situation where they're both favorable, then the reaction is going to be possible. And in a situation where neither is favorable, it's not going to be possible. The interesting situation is when one is favorable and one isn't favorable. Kind of like if one of your parents says that you can do something and one of them says that you can't. What we're going to do then to decide this situation is calculate what we call Gibbs free energy. And it combines the two factors together, but it also depends on temperature. So Gibbs free energy equals the delta H minus the temperature times the change in entropy. The temperature must be in Kelvin. Celsius doesn't work because Celsius has 0 as a legit value, which would then turn this into 0. So if you forget, Celsius plus 273 gets you Kelvin if you need to do that. When you plug the numbers into this, if you get a negative answer, your reaction is going to be overall favorable and is going to be what we consider spontaneous, meaning that it just happens. It happens spontaneously. It has enough free energy for it to happen. I'm going to do a bit of algebra here because if delta G is negative, means that that's favorable, and delta G is positive, and that's going to be not favorable. I'm interested in the boundary between favorable and the reaction happening and not favorable. And the boundary between negative and positive is 0. So I'm really going to be interested when delta G is 0, because that's going to be the boundary between favorable and unfavorable. So I'm going to substitute 0 in for delta G in this equation and solve it for temperature. Because the delta S and the delta H are just facts of life. I don't have any control over those. I do have control over temperature. So I'm solving for when delta G equals 0, because that's going to be the switching point between favorable and unfavorable. And I'm going to find out what temperature is going to land me at this boundary. Since I'm solving for temperature, and I don't want to solve for negative temperature, I'm going to add T delta S to both sides. So that this cancels. Now I would have T times delta S equals delta H. Since I'm solving for temperature, I'm going to divide by delta S on both sides. That cancels, and that's going to leave me with T equals delta H over delta S. And this is going to be the temperature when the reaction would switch from favorable to unfavorable. At this point though, I don't know if the reaction would want to have temperatures above that or temperatures below that temperature to be favorable. I just know that this is my boundary condition. And if I look on the next thing that I've provided for you here is a big summary of everything that we've done so far that's going to help us to decide if we want those temperature values to be above or below. So this is a super handy thing, and you should refer back to this chart on the worksheet that's attached for today's assignment, because it really summarizes everything. Delta H is here in this column, delta S is in this column, and this tells you what is going to be true for delta G. So I've summarized everything here. Delta H is exothermic when it's negative, and that's favorable. Delta S likes to be more disordered and is going to have a positive value, and that's favorable. So the way to read this is if the problem gives me a negative delta H and a positive delta S, what is going to be true for my delta G is this reaction is going to be, it's going to work at any temperature. My delta G is always going to be negative because these factors are both favorable, so it's going to work always. The opposite condition is when you have a positive delta H and a positive delta S. Both factors are unfavorable. So my delta G is always going to be positive, and that means my reaction is never going to be spontaneous. This is going to be something that doesn't work. And then the interesting situations are going to be when one is favorable and one is not favorable. So in this row I have a favorable delta H and an unfavorable delta S. And if I do my math on this, my temperature is going to be equal to delta H over delta S. And I'm going to want the temperature to be lower. So this is going to happen, this is going to be favorable when my temperature is less than delta H over delta S. The way I like to think about that is this is an exothermic reaction. It's trying to release heat. Is it easier to release heat into a hot environment or a cold environment? It's going to be easier to release heat into a cold environment. The opposite is going to be true if I have a positive delta H, unfavorable, and a positive delta S, which is favorable. This is going to be favorable when my temperature is above delta H over delta S. And I like to think about that as, since this is an endothermic reaction, it needs to absorb heat. And this is going to be easier when it's a hot environment. And that wraps it up. This has gone on long enough. What's attached today is a paper where I ask you to pick out the most important points from this video. So you'll find that in Google Classroom. If you need any help, please let me know. As always, take care of yourself and others, practice good hygiene, and I'll see you on the flip side.